So the thing is, I make a ton of YouTube videos for my chemistry courses, and it's weird because things fall through the crack. You make so many, and you're like, oh, surely I've made so many, I've made this video. I actually had a YouTube commenter point out that I discussed the Clasius-Clapeyron equation qualitatively and never bothered to go back and talk about it quantitatively. So thank you to the YouTube commenter for pointing out that yes, in fact, I do actually integrate a couple videos on Clasius-Clapeyron. Now, this video here is meant to frame the Clasius-Clapeyron equation, but if you're just curious in using it, this is not the video for you. This is actually going to go through the derivation of it. Now, how do we derive it? Well, this is the one you're probably used to seeing here, but what a lot of students don't realize is they see this equation and don't realize it has a ton of assumptions built into it, and it's not actually the Clasius-Clapeyron equation. This is dp dt equals delta s over delta v. So how do we jump from this to this? Actually, it's not as bad as you think. This is true at every phase boundary. So if we look at the slope on a PT phase diagram between any two phases, solid liquid, liquid gas, solid gas, we will always get this relationship. But there is a special case, and the special case is when we are looking at a gas, when we're looking at a liquid to gas transition or a solid to gas transition. So first of all, at any phase diagram, phase boundary, we have the relationship that the delta G is 0, therefore delta H minus T delta S is 0, so we get that the delta S equals the delta H over T. So walking towards this point, at a phase boundary, we can make the substitution that delta S here equals delta H. Vaporization over T delta V. Now how about this delta V term? Well, let's think about what it physically means. So if we are going from a gas to a liquid or a liquid to a gas or a solid to a gas, delta V is just literally the volume of the gas minus the volume of the liquid or the solid. We can use either in this case. But think about it this way. If I have a milliliter of liquid and I evaporate it at 1 atmosphere room temperature, what are their relative volumes? Well, if you think about it, the gas is going to occupy a lot of space, right? I mean, unless I compress it down to make it a liquid, it's going to occupy a huge volume. So what we're going to assume here is that the volume of the gas is much, much greater than the volume of whatever phase we're coming from. So really the delta V here is just the volume of the gas. And volume of the gas, these are all molar quantities, is just connected to the ideal gas equation. So if I rearrange for the volume, I get the volume equals RT over P. And when I substitute back into this equation, I get delta H of vaporization equals RT squared times the pressure. Good so far? Now, here's the clever part. We've got this relation dp dt equals delta H of vaporization B over RT squared. So dp over P is delta H of vaporization over R times dt over T squared. And I'm going to integrate both sides from P1 to P2, T1 to T2. And I'm going to need to erase over here. When I integrate this side, I get the natural log, P2 over P1 equals minus delta H, vaporization, over R, 1 over T, integrated. Sorry, I'm going to get rid of the bounds of integration here. Now, let's go ahead and work it out. 1 over T2 minus 1 over T1. Now, this is one of the most common forms of the Clausius-Clapeyron equation with this negative out front. Personally, I like to leave it out of the equations I work with. And so what I'll do is I'll distribute the negative inwards. And I'll get the relationship I have up here. The reason I like to do this is just pedagogical. I find students typically they ignore that negative sign. It's just one of the details that we inherently leave off. But this is how we come to this equation. Now, a few comments on this equation. Because of this natural log, we can do a lot of things with the negatives. So if we want to put the negative back in, we can also do it by flipping this equation around. This natural log gives us a lot of power, but this is the origin of the Clausius-Clapeyron equation. It's that dP over dt equals delta S over delta V. We plug in the ideal gas equation, we plug in the condition for delta equals 0 at the phase boundary, and this is what we end up recovering when we do the bounds of integration. So in the next video, we'll talk about practical considerations of the Clausius-Clapeyron equation and how to gauge if you've got a reasonable answer.